Come to know and love, where we have two overview talks that will lead into two separate parallel sessions. Each overview talk will give a little bit of insight into what each of the parallel sessions has to do with. So with that said, these are 15-minute talks with 5 minutes of questions and tossing around little cubes. And so the first one will be given by Jeff Plescia on new views of the Lunar Regolith.
Thank you. I hate to think that I'm the representative to start normal. Okay, Jim mentioned this earlier. Today is the anniversary of the Apollo 11 landing on the moon. For those of you that weren't even born back then, and despite any number of videos on YouTube, it actually is on the surface, and you can see the trails and the experiments. Okay, so the motivation behind this is partly the New Views of the Moon 2 book, one of which is many of the topics have been discussed, and one of them is going to deal with the sort of origin and evolution of the regolith. In that case, it's only relevant to the moon, but in the survey context, it's relevant to both the moon and small bodies. There's terrestrial definitions for what a regolith is. The sort of canonical idea for planetary, based on the early work on the moon, was that it's the debris layer on the surface of in the case of the moon, that ranges from meters to tens of meters. And in the context of the moon, the idea was it was formed by impact processes, and that it basically is the physical disaggregation of larger fragments into small ones over time, in addition to chemical changes and radiation changes. But right now, there's sort of a number of questions we can ask. How does a regolith form on airless bodies? Is it the same everywhere? Does it vary? Does it vary in time or space? Do the same processes occur everywhere? And what are the properties of the regolith, both on the moon and on different small bodies, and how do they change over time? So go back to the moon for a second. Most of the moon is covered with a relatively fine-grained debris layer. Locally, there are rocks. If you get an impact into it excavates through the debris layer, you expose rocks. Those are subsequently eroded over time by micrometeorites. Going back to Fred Hertz and Don Galt, there's all kinds of little charts like this that describe, based on different sort of fluxes, how long a rock sitting on the surface will last. And these models sort of suggest that if you got a 2-meter boulder, 99% probability that over the course of a couple 100 million years, it'll disappear. And to some extent, the exposure ages of the Apollo samples sort of agree with that. But what about asteroids? We know that depending upon where you are in the solar system, the relative impact velocity is going to be considerably lower on an asteroid than it is on the moon. The result of the lower impact velocity means you're going to have less energy to bombard the surface and break stuff up. You've got lower surface gravity, so stuff can get away easier, as well as the lower escape velocity. And this led people like Kevin Housen and Shears to suggest that small asteroids, depending upon how you model it, somewhere less than 10 or 100 kilometers, would not have regoliths, and that if you got into bigger bodies, they'd have the gravity to retain that. And what we found was that the observed geology was wrong. Just kidding. We found that even small bodies like Itokawa and Tutatis were covered with regolith, and Itokawa is only a couple 100 meters, so we know that any body that's been observed has a regolith. So the question became, what's happening? You know that both from terrestrial observations of the infrared signature as well as spacecraft observations, that there's a surface on these bodies that has a range of grain sizes. It might be centimeters to boulder-sized objects. We know from the Itokawa sample return that they're micron-sized particles. So it doesn't appear that, to first order, the surface properties are any different from the lunar regolith. It's a range of particle sizes, a range of compositions. There's monomineralic features, there's polymineralic particles. What wasn't observed in the Itokawa samples was something like an agglutinate, but given the way those samples were recovered, it could have been there and been destroyed. There are suggestions that some of the shapes of boulders on Itokawa are different from impacts, and so this sort of led to the idea that there might be thermal fatigue, which I'll come to in a minute. Now, despite the fact that you had the idea that on the moon boulders break up due to impact, you have these kind of features which are observed in this case in Schiller Crater, where the boulders rolled down a hill, and you can see the tracks here. They got to the bottom of the hill, and they just apparently fell apart. This does happen. This is the boulder on Apollo 17 at Station 6 that apparently stopped rolling down the hill because it came apart. But these are already on flat surfaces when they broke apart. And one could imagine from an impact perspective that, well, maybe just coincidentally you had something hit one of these boulders and shatter it. But to get two that are only 100 meters apart or so seems unlikely. So there's got to be another explanation for what happened in these kind of cases and how these things disaggregated from a boulder that was capable of rolling hundreds of meters down the slope, then subsequently just fell apart at the bottom. Okay, so the model was proposed that there's something called thermal fatigue, where you heat and cool surface rocks up and you generate stresses, and this can break down the rock into smaller pieces. This kind of stuff is observed on the Earth, and in fact, in 1936, a highly technical experiment was conducted where they stuck a rock in front of a heater and then blew on it with a fan to see how it would break down. People proposed this for Eros and other small bodies. Marco Delbo has done some work where he's calculated that you can crack a 1 centimeter rock on a near-Earth asteroid in 20 years, and as opposed to a micrometeorite, which will take something on the order of 20 million years to break down. Some other experiments that have been done by Charles O'Meara, who's part of the APL survey team, and KT Ramesh at Johns Hopkins, have looked at what happens when you heat and cool rocks in terms of crack propagation. And so here's two reflected view lights. Here's the area before and after thermal fatigue, and you can see that a crack is propagated. And they're beginning to model things now to look at the survival times of different size rocks over a range of scales, and as a result of actual observations of crack propagation into the interior. So clearly, thermal fatigue is a relevant mechanism. The question is whether it works on just asteroids, whether it also works on the moon. Jamie Molinaro has done some studies where he looked at the compression and tension induced by thermal stresses over the course of a day on the moon, and you can see they become quite high, and you can certainly fracture a rock with those kind of stresses. Also looked at what happens as a function of distance in the solar system. This is from 0 to 2.5 AU, and the period in days and the kind of stresses you can generate are in color here. This is for the whole block, and this second chart is just down in the area right in here. And you can see that you really don't get very high stresses unless you're very close to the sun, which we're not, and that you get out in the outer part of the terrestrial environment, and the stresses are small, but they're still on the order of several hundred megapascals, enough to shatter a rock. One of the questions is, how far does this go in terms of breaking sizes down? You can imagine a big boulder that's got shading and stuff, and where you can get stresses induced. Eventually, though, you get down to a particle size that's small enough that it becomes isothermal. And the question is, how does this work at very small scales? And that's something that's yet to be investigated. Just to go back to the moon for a second, in terms of what do we know, the canonical model looks like this, where you've got a surface regolith. In the case of the highlands, over some mega regolith that's impact basin generated over fractured crust. If you're on the Mare, you got a regolith over some Mare lavas, which is overlies mega regolith from the basins, and then you get down into fractured crust. That seems to be the view that was observed, at least on the Mare. Looking in Hadley Rill here, looking across the rill, you could see a regolith surface, then some basalt underneath, and then either buried regolith or just loose material, and then basalt at depth, which sort of looks like this model. So that part of the model, at least the basic structure, appears to be valid for the moon, as well as from the observations and seismic data. What we know about the physical properties, though, is relatively limited in terms of depth. There were sort of casual observations made at the surface during Apollo, as well as some of the earlier robotic missions. There were some cores that were taken and some cone penetrometer measurements. Those extended down, a couple of meters at most. We really don't know what happens below that. So the basic sort of grain analysis and density and bulk composition, all this stuff, this really hasn't changed very much since the days of the Apollo program. The density structure looks something like this. The question is whether there's a uniform increase in density or whether there's in fact discrete layers. One of the things that was observed in the Apollo mission was that there are in fact any number of discrete layers in the surface. You see that in the core data. You see that in the seismic velocity data. You see that in the cone penetrometer data. There's lots and lots of layers that extend only a short distance. One of the things that was observed in the Changa Rover mission, here's the rover sitting here. It took a short foray south, then turned around and came north, and that was sort of the extent of the mission. Zoomed up here, this is what it looked like. The rover had a GPR, ground penetrating radar, to look at what the subsurface structure looked like, and what it revealed was some picture that looked like this, where you had a very thin superficial layer, an intermediate layer, and then a couple deeper layers, as well as lots of little scatterers. And the suggestion was that this is the the rover landed on the edge of a much larger crater here. So this is the regolith that's developed since this crater formed. This is the ejecta from the crater. Below that, underneath that is the regolith layer from the mare on which it sits, and then below that is the sort of underlying mare surface. At least that's a plausible explanation for this, but remember, this is a very short profile in already a complex environment. But it does suggest that there's lots of discrete layers that extend only a short distance away from each crater. You can imagine the situation like this, where at the landing site, you got ejected from this crater, ejected from this crater, and ejected from this crater, all superimposed, but extending only a short distance. So where are the rocks that are forming the regolith come from? Well, they come from impacts primarily where you expose rocks to the surface. This is at the Changa landing site. These rocks were excavated by this crater in the background here. Camelot crater, the rocks in the foreground came out of this one. They're also coming out of just general exposures on hillsides and in rills. Here's the edge of Hadley Rill. You can see the continuous layers of basalt here, and you can see a bunch of rocks on the bottom. What we've been looking at is the size distribution of the rocks on the bottom to kind of understand something about the fracture spacing in the original mare. The rocks would be pre-fractured by stresses, and so the original target rocks that you would subsequently degrade would already be smaller than some size based on the fracture spacing, and so we're trying to understand what that is. One of the other things is try to understand what the complete size frequency distribution of material is on the moon. We have samples that were brought back by Apollo, which cover the very small size down here, where we're talking about stuff that's less than pretty much a centimeter or so. You've got images from the surface, like at Surveyor and some of the lunar Apollo missions, which give you data from here, and then you've got orbital data to give you data out here. And so we're trying to construct what a complete size frequency distribution might look like if you were somehow able to bring back several cubic kilometers of the regolith and then just sort it out by size. And it suggests that the data from a variety of different things that have been sort of scaled up and down suggests something like this, where there appear to be some discrete bends in the distribution at different sizes in boulders and at different sizes at smaller particles. So we're trying to look at a variety of different places to understand whether this is just an artifact or whether this is real. This may reflect compositional features. When you get down to very small sizes, in the regolith samples, there's a discrete change in the composition at different sizes because different kind of particles have different strengths. The size out here may be reflecting differences in the fracture patterns, and so understanding what this original sort of size distribution is, which has already been evolved somewhat, to understand what the original size frequency distribution in the regolith is and how that's evolved. Another aspect that's become interesting is the gardening rate and the exposure of immature material on the surface. LRO has observed a number of impact craters that have formed where there's an image of an area before and after an impact, and you can see the crater and you can see ejecta extending out. There's lots of little secondaries as well as little tiny splotches. When you look at this kind of stuff, you see the size frequency distribution of craters and these splotches, which in some cases are resolved secondaries, in other cases are just albedo marks, which may or may not be well-defined craters at below the resolution limit. There are low reflectance changes and high reflectance and mixed, which suggests that you're turning over both immature and mature regolith in these events. Now, the question is how does this tell you about the excavation rate and how material is turned over? From the work that Emerson Spreyer has done, this suggests that you're turning over material to a depth of 2 centimeters on the order of 10 to the 4 years, and maybe to 20 centimeters over 10 to the 7 years. This, 1 minute. Ooh. All right, this suggests, quote Bob Strum, oh my God. This is orders of magnitude faster than the conventional rates that Don Galt and Becky Gent have seen. There's a lot of unknowns left. We've made a lot of progress. Most of the recent progress has been made in understanding what's going on in the upper few centimeters or tens of centimeters based on the LRO photometry and the thermal data. All right, I'll put there.
Time for a few questions. Throw right over somebody's head.
You have the crater that was produced and seen by LRO.
Mm-hmm.
Has LRO gone back a couple years later to see if there was any aging of the new ejecta visible?
In a few cases, yes, and nothing obvious has changed. That's part of the so-called cornerstone mission, is to examine some of the craters and landslides that have been observed to see how they evolve over time. But we know, we can clearly see the tracks and the disturbance from Apollo, which is 40 or 50 years old, which suggests that the time rate is pretty low. But we'll look. Mihai?
Wait till you get the cube.
All right.
The latitudinal variation, is that not something to do with the distribution of Maria?
No. The effects are beyond the Mare. They occur all the way around the moon. So the latitude effects?
Yeah. You got the Procellarum coming all the way down into the southern hemisphere.
But it's a global.
But you're averaging around the moon, right?
For the mini RF data, averaging all the way around the moon. So on the far side, it's highlands. Now,
Right.
in talking to Brad Thompson, who did the work, I asked him if he had, in fact, split it up into longitude bands. In which case, the front side might look very different from the far side because of the Mare symmetry. It also might change because when you get up towards the poles, there are a lot of permanently shadowed craters. And if that were somehow a reflection of permanent shading, you might, if you could sort out that way, you might see that as well.
I just wanted to get this. Early on in your talk, you mentioned that there is a big difference with the impact speed of interplanetary dust particles hitting the moon versus an asteroid. I wonder, where would that come from? Why is that?
Where's Bill Botke? It's a dynamic thing based on where you are in the solar system. The impact velocities vary. Blame Isaac Newton.
The orbital velocities are larger at the moon. The orbital velocities are larger closer to the sun. Plus, the debris in the asteroids could have been there and stayed on small, low eccentricity orbits, whereas to get into the inner solar system,
Yes.
it probably is crossing the asteroid.
So this is your expectation then around 1 AU, all asteroids and the moon are roughly hit by the same sort of speeds.
Yes.
Okay.
I'd like to, there he is. I'd like to invoke the session chair's prerogative and ask one more question quickly. So you talked a little bit about regoliths on asteroids as well. And so for a relatively quickly tumbling asteroid, you may have a high frequency of thermal going up and down, but the amplitude may not be so big. Whereas on the moon, you'll have a large amplitude and small frequency. Which one will contribute more to degradation of rocks over time?
Well, the bigger the amplitude and the higher the frequency, the more damage you're going to create.
Sure.
So on an asteroid, it is going to vary depending upon where the pole is You know, you could have, if the pole is staring at the sun, there's essentially no
Sure,
change.
but assuming it's, yeah.
And there's a whole suite of analysis, and I don't remember the details as to exactly when, but obviously the higher the amplitude of the thermal cycling, the larger the stresses you're going to generate. So the closer in you are, the better. But the idea, though, is that even at main belt asteroid distances, the effect is sufficiently large to work faster than the micrometeorite bombardment.
So perhaps what you're saying is amplitude is more important than frequency for